Hey everyone, and welcome back to Physics 101. Today we're going to be looking at motion equations. They're right over here on the right hand side, as they're often called the CVAT equations. Um, but before we get into those, I'm quickly going to go over something I wasn't able to fit into my last video, which is uh, having negative values in velocity versus time graphs. So essentially, there will be times where you are given a velocity time graph or an acceleration time graph, and the values are underneath the x-axis or appear negative. What this means is not that the velocity is increasing or decreasing, or the acceleration is increasing or decreasing. What it means is that the velocity is in the negative direction, or the acceleration is in the negative direction. So for example, if someone is walking from left to right, which is generally considered positive, their velocity time graph would look like this, wherein it's a constant velocity and it's in the positive region of the graph. However, if they are then, let's say they turn around and go from right to left, then their velocity time graph will look like this, in the negative region of the graph. And this can apply to any graph, acceleration or distance time graph. You will not need, it will not mean that there is a deceleration or a decrease in velocity. What it means is that it's in the negative direction if it's underneath the x-axis. Uh, so yeah, lastly, these two graphs here on the right show you how an increase in velocity doesn't mean it's negative if it's underneath the x-axis. It's just in the negative direction. And again, here we are with acceleration and distance. They can apply with the same principles. If it's underneath the x-axis, then it is just simply in the negative direction, which can be anything you want, but usually it's right to left or up to down. Right, so back to the equations here. We have our four equations. Now these equations are derived from the equations we made last video, like v equals change in d over change in t. And the one for acceleration and distance, etc. So these are derived equations. Now, you don't need to memorize these four equations, mainly because obviously that would be quite hard. And if you are taking a physics exam or test or whatever, most of the time you'll be given a formula sheet because there's so many in physics, and these four are very likely to be included. I've pulled this image straight from the IB physics data booklet because they have all the necessary formulas and they lay it out quite nicely. The IB is a high school program for years 11 and 12, and they have a very good physics course. So we'll see multiple uh, items pulled from their database, including this question here, which we're going to go over in a sec. But anyway, we have our four equations, and we have the variables listed here. This is a bit cut off, but you can see t is time, a is acceleration, distance, initial and final velocity. So since we are going to have these equations at our disposal to look at and not need to remember or memorize, we're just going to jump in straight to a question just to get the hang of using these equations. So let's go over this this question here. A ball starts from rest and moves horizontally. 6 positions of the ball are shown at time intervals of 1.0 milliseconds. Now this can be confusing if you're just starting to learn physics. You'll see milliseconds here. Now you might be thrown off by this. You might have read this as meters second, or you might have been confused because you've seen in the previous video and maybe seen before velocity measured in meters and seconds, so this could be confusing. But as we see time intervals, you should be able to get an idea that this has something to do with time, nothing with velocity. And I haven't explained so yet, but this is milliseconds. We'll go over converting units throughout. I don't think I need to make an entire video on it because it's very basic, and I'll show you how to do it quite easily as we go through the question. So anyway, six positions of the ball are shown at time intervals of 1.0 milliseconds. The horizontal distance between x, which is the initial position, and y, the final, is 0.05 meters. What is the average acceleration of the ball between x and y? Okay, so I think I forgot to mention, which is quite important, these four equations here can only be used when there is uniform acceleration. Now what that means is we are either trying to find an acceleration that is an average or an acceleration that is constant. So here we're finding the average acceleration. So this we are able to use these equations. If we had to find the acceleration at one stage or another where we have a changing acceleration, we would not be able to use these equations. So if it was asking for us to find the acceleration at a certain time and that acceleration is not constant, we would not be able to use these equations. But luckily, we are trying to find the average acceleration of the ball, so we can use these equations. So let's get started. So we are always going to find the most important information in the question. The question will give us what we need to know. So straight from the first sentence, a ball starts from rest. Let's stop right there. We know straight away from these, that's going to tell us the initial velocity is going to be 0. If a ball is starting from rest, that means it's not going to be moving at the start. So let's just write here u equals. So the average acceleration of the ball, right? So our initial velocity is going to be 0. If the ball is starting from rest, we know the initial velocity is going to be 0. What next? So moves horizontally. 6 positions of the ball are shown at time intervals of 1.0 milliseconds. Okay, so that's going to tell us that we're going to be able to find out the time it takes for this occurrence. So 6 positions, 1, 2, 3, 4, 5, 6, right, are shown time intervals of 1.0 milliseconds. Now we see here at x, this might have thrown you off if you tried this already, but at x we already have our first time interval, and then second starts here, and our third here, etc. So the first one here isn't really one of the positions we're concerned about because it is the start. We already know that at the start the ball's not moving. So these 5, we're going to ignore this one. These 5 here, as the ball moves, are the ones that we are concerned with. So if they are constant time intervals of 1.0 milliseconds, then we know the whole time it takes for this ball to go across from x to y is going to be 5 milliseconds. Now I'm going to leave this as 5 milliseconds just for now, but we are going to have to convert this. Whenever you're given units like milliseconds, nanoseconds, gigaseconds, whatever, you have to put it into seconds. Normal, just plain old seconds. That's because when you're trying to find acceleration, well, acceleration is meters per second squared, not meters per millisecond squared. So we're going to have to convert this, but we'll do that later. Let's just find the rest of the variables. The horizontal distance between x and y is 0.05 meters. So that's pretty easy. Our distance is 0.05. Okay. So now our acceleration, that's what we're trying to find. So we'll write a equals question mark, and we'll leave that here, and we'll find the appropriate formula to use out of these 4. So we have u, t, and s, and we're trying to find an a. So clearly we don't know what v is, we don't know what the final velocity is, we weren't given it, so we're going to choose one of these formulas that doesn't have v involved, otherwise we won't be able to solve it. So here we see this is the equation that does not have it does not have final velocity as a variable. So this equation is what we're going to use to find the average acceleration. So let's plug in the variables. So we have s, which is, we know it's 0.05 equals ut. So u is 0. So you probably already realized that this little part here is going to be 0, but we'll just write it down anyway. So 0 times t. Now, like I said, we have to convert this. So let's convert this quickly. 5 milliseconds. So milliseconds, I probably could have made a video on unit conversions, but in a formula booklet, not only will you get formulas like this, but you should be able to get a unit conversion image which shows you what milliseconds equals and microseconds, etc. But you'll pick it up along the way. It's not very hard. If you don't know already, milliseconds, I'm just going to write this down here just to make sense. So 5 milliseconds is the exact same thing as 5 times 10 to the power of negative 3 seconds. So this means the same thing. So since we need our units in seconds, we're going to write this out for this part of the equation. So 5 times 10 to the power of negative 3. So straight away we already know that this is going to be 0 because anything times 0 is 0, but we'll just leave that in there. And then we have plus, I'm just going to write half as 0.5 just to make things a bit easier, times a, we don't know what a is, but we're going to find it, and then times t squared. So 5 times 10 to the power of negative 3 squared. So we'll just make this easier, especially for plugging into the calculator. Now to make this even easier, let's just convert this into a decimal. So 5 times 10 to the power of negative 3. Right, so that's going to be 5.0. I'm going to move this over 3 times. 1, 2, 3. So we have 0.005. Okay, so now that we have this, let's rewrite it one more time. Just a bit easier. Equals, that's 0, so we'll have 0.5a times 0.005 squared. Okay, so here's our formula. Now we just got to find a. Now this is pretty easy. What we're going to do is just divide both sides by, we're going to get a on its own, so we're going to divide both sides by 0.005 squared. So let's get the calculator up. So if you want to do this on your own, 0.05 divided by 0.005 squared. And we get answer as 2,000. So now we have 2,000 equals 0.5a. And finally, now we just have to divide both sides by 0.5, which is pretty much the same as timesing it by 2. And what we get is 4,000. So let me just make space here. Get rid of it. Sorry, hold on. Let me just get rid of this here. So we are left with A equals 4,000. And we look at the answers here, and we have B as our answer, and B is the correct answer. So this was just a demonstration of using the SUVAT equations. There are some more complex ones we can do. I thought this one was quite easy and quite intuitive. So we're going to leave it at that and look into possibly more questions, or maybe move on to the next chapter. But yeah, so the SUVAT equations are quite easy to use, and you should have them in the formula booklet. If you don't, that's a problem. I don't know why you wouldn't be given them. Alright, well, thank you. Leave a like and subscribe, and I'll see you all in the next video. Bye.